Next, we want to talk about cones and projective varieties, because we have seen in the previous video that the affine and the projective vanishing locus of a set of homogeneous polynomials encode very similar information. And here we want to make these precise, give some definitions, and then a correspondence essentially. Because this will allow us to transfer information about the affine variety, which we already know a lot about, to this projective variety. And the crucial definition is the one of what it actually means to be a cone. So for this, look at this projection map from an plus 1 minus 0 to pn, which is just take this vector and gives this element of pn given by these homogeneous coordinates. Then an affine variety inside an plus 1 is called a cone if it contains 0, the origin, and it has the property that when x is an element of big X and lambda is a scalar, then also lambda times x is in X. So in other words, it's invariant under scaling with elements of the field. And if you have the second condition, in fact, asserting that 0 is in X is equivalent to saying that X shouldn't be the empty set, because once you have any element of X, then 0 times X, so the origin is also in X. So that is what we really mean by cone in this lecture. And then, given such a cone, we can define its projectivization just as the image of X minus the origin under this map here. And if you spell this out using this projection map, it's just the set of all such points inside Pn, such that if you place commas here, then it is in X. And so this starts with a cone and gives something, some subset of Pn. In a second, we're going to see this subset is a projective variety. And similarly, in the other direction, if you start with a projective variety, then you can define the cone over X as, well, you have to manually input the origin plus the pre-image of X, again, under this projection map. So you have a subset here, you take the pre-image. And again, spelling this out, this is a set of such vectors such that the corresponding homogeneous element of the projective space is contained in X. So this cone now sits inside an plus 1. And again, below we are going to show that this is a cone in the sense of this part A. Before we do that, before we go to our correspondence result, let's see a remark which connects these cones to kind of a third object, namely ideals, in particular homogeneous ideals. So the first part is that if S is any set of non-constant homogeneous polynomials, none of the elements here is a constant such polynomial, then the claim is the affine vanishing locus of S is a cone. And well, for this, you just observe that any non-constant homogeneous polynomial, so it cannot be 0, it cannot be constant, non-zero. So it must be of degree at least 1. And then once you're of degree at least 1, if you plug in 0, you get 0. And so all of these things vanish at 0. And so we verify the first condition, that the origin is contained in the affine vanishing locus. And then if you have lambda and k and x in the vanishing locus, then, well, by definition, f of x is 0 for all f in this set S. And then we want to show that lambda times x is in the vanishing locus. For this, we just calculate that f of lambda times x, well, you can draw it out, it's lambda to the degree of f times f of x. This was 0, so this is 0. And so we have checked, indeed, all of these polynomials also vanish on lambda times x. So lambda times x is still in the vanishing locus. And we have checked the two conditions of being a cone. So homogeneous polynomials cut out cones. And then conversely, if you start with a cone, the claim is that the usual ideal of this subset of affine space inside here is in fact a homogeneous ideal. So this goes in the opposite direction. And for this, we're going to use this criterion that we have seen before. So an ideal is homogeneous if and only if for every element, also all the homogeneous components are in the ideal. So if you have an element here decomposing like this, it suffices to show that all the individual homogeneous terms are again in the ideal. And so for this, well, we want to use the property of being a cone. So when lambda, when x is in x and lambda is a scalar, then we know lambda times x is in x. And so given this polynomial, of course, it vanishes on all of x. And so in particular, it vanishes at this lambda times x for all lambda. So we just write down this condition that 0 is equal to f of lambda times x for all lambda and k. But using this representation here, we can actually expand this. We plug in this, this sum, and then we see that fd of lambda times x is just lambda to the d times fd of x. So for the different degree parts of f, you get different powers of this parameter lambda out. And now we look at this equation that 0 is equal to this sum here for all lambda and k. Then we can see this here actually as a polynomial in this single variable lambda. These are here are all numbers. These are the coefficients of the polynomial. And this is the different monomials in lambda. And so here we have a polynomial in a single variable over k, which vanishes at all points of this field k. And then since k is algebraically closed, in particular k is infinite, a polynomial vanishing at all points has infinitely many zeros. The only such polynomial is the zero polynomial. So in fact, this must be the zero polynomial, so all the coefficients must vanish. And this is exactly what we wanted to show, that all of the fd's are still in I of x. So, so here we showed that somehow being invariant under the scaling then actually forces all the individual degree parts to also vanish. Okay, so this was a bit of preparation connecting cones to homogeneous ideals. And now we can actually come to the lemma. And this tells us that there is a bijection between the set of all cones inside an plus 1 and the set of all projective varieties inside Pn. And the correspondence takes the cone x to its projectivization and the projective variety to the cone over it. So that's kind of a perfect translation. And it tells us that these affine varieties, these cones, basically allow us to describe the corresponding projective varieties. As a first step, what we should do is we should show that this correspondence is indeed well defined, because so this means we should at least check that the projectivization is a projective variety and that the cone over y is actually a cone. So we'll do these two directions. Let's start with x being a cone. Then, by the remark that we had before, the vanishing ideal of x, let's call it j, is a homogeneous ideal. And now we have to do a slight dance. So you'll see in a second what I mean. So we have this homogeneous ideal. And so we can define S to be the set of homogeneous polynomials inside J. And then, because it's a homogeneous ideal, it's generated by its homogeneous elements. So J is equal to the ideal generated by S. And then, well, what we know about X, the thing that we started with, is X is the vanishing locus of its ideal. That was part of the original Nullstellensatz. But then this ideal J is generated by S, so equivalently we can go to the vanishing locus of S. So here we started with the ideal, now we went to a set of homogeneous polynomials. Keep that in mind. And then we look at what is the projectivization of X. Well, it's a set of points in projective space such that the corresponding vector here is in X. But being in X, we have seen, we use this equality here. This is equivalent to saying f of x is 0 for all f in S in the set of homogeneous elements. But now we're in business, because if you look now what we have written here, it's a set of points in projective space such that a set of homogeneous polynomials vanish there. That's great because that is the projective vanishing locus of S. And now we can go the opposite direction. We can see the vanishing locus of a set S is the same thing as the vanishing locus of the ideal generated by S, but the ideal generated by S was J. And so we're back to J. So here we had to do this little dance. We started with the ideal, then we had to go to the set of homogeneous polynomials such that we could write down this equation here nicely. And then afterwards, we could go back to the ideal. But anyway, so somehow what we have seen with this little argument is that the projectivization of X has this form. And so by definition, it is a projective variety. And we have actually already seen that it is exactly the projective variety associated to this homogeneous ideal. So that was one direction. The other is we start with a projective variety. We want to show that C of Y is then a cone. So let's say Y is such a projective variety given by the vanishing locus of some homogeneous ideal. Then the cone of Y, by definition, is the union of the origin with the pre-image of Y under this projection map. And we saw this pre-image is the set of points here such that corresponding homogeneous vector is in J. But then now we use the kind of corresponding equivalence. So being in Y is equivalent to all of the polynomials in J vanishing at this point. And now we have to do a little case distinction. And I mean, when you talk about these projective varieties, unfortunately, you often have to distinguish kind of two cases. So because what we secretly want to do, instead of having this union, we would like to draw this zero inside of this set. So we basically want to say that this is actually just given by the set of these X in, so basically by such a vanishing locus. And so there's two cases to distinguish. The first of all, if J contains a non-zero constant polynomial, like 1, for example, then, of course, it can never happen that F is 0 at any of these points here, because 1 never vanishes. And so this entire part here is empty. And so we just get the first part, we just get 0. On the other hand, if J does not contain non-zero constant polynomials, then all the polynomials it contains are either the 0 polynomial or homogeneous polynomials of degree at least 1. And we saw those things vanish at the origin automatically. And so the claim is then this is actually just equal to the affine vanishing locus of J, because, well, this is the affine vanishing locus of J minus the origin, but the origin is automatically then contained in there, so this is just the entire vanishing locus. So here we had to distinguish these two cases, but we have now given the characterization, the cone over Y is either 0 or this affine vanishing locus. And both of these are cones in the sense of above. I mean, 0 is clearly a cone, and we have seen, this was the other part of the remark above, that the vanishing locus of a homogeneous ideal is a cone, if that cone contains no non-zero constant polynomials. Okay, and so both of these are cones, so we're done checking that that this is indeed a well-defined back and forth map. And now we only have to show that the two compositions give the identity. But with the preparations that we have done, that is actually pretty easy. So notation we keep as above. So let's say we take a cone over the projectivization of X. Then, well, the projectivization of X is given by the projective vanishing locus of the affine ideal of X. So here we just plugged in what we saw in this first part of the proof. And since X, the cone, is by definition non-empty, this I of A contains no non-zero constant polynomials. Otherwise, X would have to be empty. And so now we want to compute a cone of something, but now we are in business because we are in this second part. And so we can replace cone of projective vanishing set. So Y was a projective vanishing set like this. So we can compute this part here to be just the affine vanishing locus of this ideal. And then again, by the Nullstellen, that's VA of IA is equal to the identity. So we get X. And so that was what we want to show. This composition here is the identity. And the other direction is actually even a bit easier. The projectivization of the cone of Y, there we can just plug in the definition. So here it's, so this is the cone over Y was defined as taking the preimage of Y union 0, and then the projectivization was take the 0 out again and project under this pi, under this map here. And so we can kind of putting in 0 and taking out again, we can basically ignore. And so we just have this form. But then this projection map is a surjective map. And for such a surjective map, it's always true that if you take a preimage and then take the image again, you just don't change the set. And so we indeed get Y back. And this proves the second part of the bidirectivity. So here in this video, we have seen projective varieties correspond to cone in the affine space AN+1. And now in the next part, we're going to see we can use this correspondence to prove a variant of the Nullstellen Satz for projective varieties.